Hello, stats fans, and welcome to part 2. We did part 1 last week, if you recall, of our statistical lecture for this week. And the lecture this week is going to be on inference and populations and samples. So let's talk a little bit about what I mean by that. Basically, here are some examples of probability in social research. Last week we talked about probability as if it were in a vacuum. We talked about how to figure out probability for cards coming out of a deck and different other things. But this week we're going to talk about what it really means. Probability is something that we use all the time in social science. So let's say we have information about a state-level recidivism program, okay? We want to find out what groups have a greater probability of recidivating. So in other words, what groups, whether they be females, males, 18-year-olds, have a greater probability of recidivating in crime. All right, so that's something. So we figure out the probability of that. Another example is we have an information about national high school dropout rates, right? And we want to study the probability of dropping out of high school among a sample of youths in a given neighborhood. So do youths in a urban neighborhood have a greater probability of dropping out of school, for instance, than youths in a suburban neighborhood? And finally, you have information about a job placement rates among UNH students. We want to find out, we want to investigate if UNH students' probability of finding employment after school is greater than the probability of other colleges' students finding employment after they graduate from school. So you get it, probability in social science really means something. It's not just all those silly formulas that we looked at last week. Inferential statistics means that we are inferring something from our statistics. So we looked formerly just at descriptive statistics, the mean, the mode, the median, and now we're going to begin to look at inferring something from something else. And what are those two things? Well, we're going to infer. We're going to take a sample, okay, and we're going to infer using inferential statistics a fact about the population, and the probability comes in where we will whether how much of a chance or probability do we have of being right. Okay, so we use inferential statistics to figure out from a small sample what's happening in a larger population, and the probability is the chance we have of being correct. Got it? Okay, so what results, and I have a little call out here, what results are likely to be found in a sample drawn from a population? And our inferential statistics are rules and formulas to determine whether an outcome found in the sample allows us to make conclusions about the entire population. Here's an example. Let's say this is probability. All right, these two things are different, don't forget. So let's say in probability there's a jar with 50 black and 50 red marbles, and we select a sample of 10 marbles. What's the likelihood of obtaining 4 black and 6 red marbles? That's what we just did last week. In inferential statistics, what we're doing is we take 10 marbles out of a jar and get 9 red and 1 black marble. That's our sample, right? How likely is it that you got these marbles from a jar with 50 red and 50 black marbles? Okay, chances are it's not likely, right? Because we took 10 marbles out, which is a sample, and we got more reds. So we're going to infer that there are more reds in the jar than there are blacks. And let's pop over to the next one. Inferential statistics, statistical inference, is the process that allows the generalization of findings from a sample to a population. Okay, so we are generalizing from a sample back again to a entire population. Okay, so we're generalizing facts and figures from a sample all the way over to a population. A sample is simply a subgroup of a population. Random sampling is the gold standard that we use to do experiments. All right, in order to generalize findings from the sample to the population, the sample must be representative of the general population. So let's say that we are taking we want to do a survey on restaurants, okay, and we go out and not a survey on restaurants, but an experiment on what restaurants charge for food. So we go out and we generally randomly sample. We don't want to go into a particular neighborhood that has, for instance, an Italian population. We got a lot of Italian restaurants, or a Chinese population. We get a lot of Chinese restaurants. Okay, we want to go to both of those and randomly sample. So we get samples from each. And the only way to achieve this is using probabilistic or random sampling. Okay, so we go out and we walk out onto a street or into a mall, and we say to people, "Hey, would you like to be part of an experiment?" All right, and we don't stop every third person. We stop every person. We don't stop every woman. We don't stop people just with hats. Okay, we randomly sample the whole of the people that we have available to us. All right, and the ability to generalize findings from the sample to the external population is a very important concept known as external validity. And I want you to remember that, because generalization, we generalize from the sample to the population, and that's what we're looking to do with as little error as possible. And if we are able to do that, it is said that our experiment has external validity. What is a probabilistic or a random sample? Random selection of observations in the sample is based entirely on chance. Each observation has an equal chance of being selected in the sample. Okay, remember those people in the mall? Each one has as they're walking by us, as an equal sample. We're not just equal opportunity. We're not just picking people with hats. The objective of all this is to maximize the probability that findings from the sample will be correct. All right, that means that they can be generalized back to the population. This is absolutely essential to being able to infer facts from statistics. Graviter and Wallnow give us the textbook definition, and it says a random sample requires that each individual in the population has an equal chance of being selected. That's the third time we're saying that, so it must be important, right? A second requirement necessary for many statistical formulas states that the probability must stay constant from one selection to the next if more than one individual is selected. All right, remember conditional probabilities? That's what this is talking about. Here are the two conditions. Each individual in the population has an equal chance of being selected. That's important, and that's the one that we always use, is that conditional probability. The other one is probability must stay constant from one selection to the next. We don't always do that because it's just not practical in real life. So this is how we address the second condition. Technically, we should replace the sample before you make a new selection. All right, we go to the mall and we pick one person and we change everybody in the mall. No, it's not going to work. So in practice, it's quite common to define random sampling without the requirement of constant probabilities. But the first condition, don't forget, the first condition back here, each individual in the population has an equal chance of being selected. That is crucial to random sampling. Okay, we need to do that. The second one, we can't always do it. Here are two types of probabilistic or random samples. The simple random sample, which units are selected on a completely random basis. Go back to the mall and just pick people at random. A stratified random sampling is selection of units within a specified group or strata. Okay, stratas, if you think about stratas, the stratosphere, do you ever hear of that? Well, those are layers in air. Okay, so if you look, you make layers like this, and well, let's say that the 18, which I have up on the screen, to 25-year-olds is in this strata. Okay, S-T-R-A-T-A. Okay, strata is in that layer or that strata, and the alternative to using stratified sampling is non-probabilistic sampling, and this is called a convenience sample or a non-random sample. Let's say that I'm doing an experiment with cops. Okay, I'm not going to go out and randomly select people. I'm going to do a convenience sample with just cops. What does that do? That limits our generalizability to an entire population. But within the strata that we're looking for, or looking in, it is a convenience sample, so it works out for us. Okay, I'm going to stop here at 11 minutes and pop over to the sampling distribution, which is part 3. So I'll see you at the next video.